I have the integral of 2 all over the quantity x squared plus 9 dx. Now what I'm going to do off to the side is remind us of a special antiderivative, that the integral of 1 over x squared plus a squared dx is equal to 1 over a arctangent of x over a plus c. Now, with our problem, we have a 2 in the numerator, but we can take that 2, that constant multiple, and factor it out of the integral. So I have 2 times the integral of 1 over x squared plus 3 squared dx. So now I can apply this general antiderivative and end up with that 2 in the front, and what's going to join it is 1 over a, which is 1 over 3. So 1 over 3 arctangent of x over 3 plus c. So I have 2/3 arctangent of x over 3 plus c. And do remember that arctangent is alternative notation for tangent inverse, so either one is fine here. Now we have the integral of cotangent squared theta d theta. So we're thinking of a general antiderivative. What do I have to take the derivative of to get cotangent squared theta? Well, there isn't a general antiderivative of this, but when I see especially a trig function squared, I should be thinking about Pythagorean identities. So I can rewrite cotangent squared theta with its equivalent Pythagorean identity, cosecant squared theta minus 1 d theta. So now I have two terms, and I can think about each one separately for its antiderivative. So what do I have to take the derivative of to get cosecant squared theta? Well, that's going to be negative cotangent theta, because the derivative of cotangent is negative cosecant squared theta, and so we need an extra negative there. And then the antiderivative of 1 would just be theta. So we're going to have minus theta plus c. I have the integral now of 3 to the t times the quantity 1 minus 2 to the t dt. So I have a product. I cannot find the antiderivative of each piece of a product separately. So what I want to do here is distribute the 3 to the t into the binomial, the two terms that I have here. So that's going to leave me with 3 to the t times 1, which is 3 to the t, minus 3 to the t times 2 to the t dt. Now here, 3 to the t times 2 to the t, since they're both raised to the same exponent, I can multiply their bases together. So what I have is the integral of 3 to the t minus 6 to the t dt. So now I have these two terms that are subtracted. I can find the antiderivative of each one separately. And so the antiderivative of a general exponential, which is what I have in each term, is going to be 3 to the t divided by natural log of the base, and then minus 6 to the t divided by natural log of the base, plus c. So 3 to the t over natural log 3 minus 6 to the t over natural log 6 plus c. Now, if you want just a brief explanation as to why we can combine these together in those rules of exponents, recall that if I have a times b to the x, that's the same as a to the x times b to the x. So we're essentially going in reverse here. We had 3 to the t times 2 to the t, so both of those exponents up there were t, and we multiplied the two bases back together, so that 3 times 2 is 6.